Hello everyone. Hey guys, this is Megha, your J educator, and today in this session we will be covering the atomic radii and its variations. This topic has been taken from the chapter Classification of Elements and Periodicity in Properties. Okay. So yes, this is from your class 11th NCRT, and this session is going to be helpful for every aspirant, whether you are preparing for JEE or NEET or any other competitive exam. Guys, here in this session we will be covering the atomic size. What is the size of an atom? How we can determine it? What are the types of radii? We do have four different types of radii, so we'll have a discussion on that. General trend of atomic radii. What will happen when we will be moving from left to right along a period, and what will happen when we will be moving from top to bottom along a group. Okay. The irregularity, yeah, many of you call them as an exceptional cases. Okay, so let's have a look that what are those irregularities that we could see in the group number 13 elements. So this is our group number 13 elements. So here in this group number 13 elements we do have a irregularity. So what is it, and how we can explain it, we'll have a discussion on this. Irregularity in the 3D transition series. If you would look for this particular 3D transition series, yes, here also we do have a irregularity. There is a irregularity in the 4D and 5D transition series. If you would compare between the 4D and the 5D transition series elements together, yes, there also we see a kind of a regularity which is not obeying the general trend of the atomic radii. Okay, so let's start with this session, guys. So the first point, what is atomic size? The size of an atom can be defined by the distance between the nucleus and the last shell electron. We do have so many number of electrons in different shells, but the size of an atom can only be determined by the distance between the nucleus and the last shell electron. Okay, so we need to know that where this electron is present. Now the question is, do we know the position of this electron? Actually no, not. Why? Because the electron is having a wave nature, and because of this wave nature the position of electron is very uncertain. So when the position is very uncertain, it's very difficult for us to determine the exact atomic size of any atom, because the electron could be either close to the nucleus or either it could be away from the nucleus. So the exact radii cannot, exact distance between the nucleus and the electron can never be determined. So to overcome this situation, to overcome this, we do have four types of radii. We have four types of radii. Okay, so what are these radii? Let's have a look, guys. We do have a covalent radii, the metallic radii, the van der Waals radii, and the ionic radii. Okay, so how these radii will be helping us in determining the size of an atom? Let's see. The covalent radii, in the covalent compounds. So when you will be talking about the covalent compounds, the compounds like HCl, HI, wherever we will be having the covalent bond formation H2, or let's say you are talking about the Cl2 molecule, they all have a covalent bonding, they all have a sharing of electrons. So whenever we will be talking about such compounds which do have a covalent bond formation, let's say this is my chlorine and this is my chlorine, and they both are sharing their electron, and because of this sharing there is an overlap of orbital. There is an overlap. When there will be an overlap, the distance between the nucleus of this chlorine atom and the distance between the nucleus of this chlorine atom will be said to be d. Okay, this distance will be said to be d. So if we want to know the radii or the atomic size of a chlorine, we will be doing d by 2. That is the half of the distance between the two nuclei of two atoms of one covalent molecule. Got it? Now, what do you mean by the metallic radii? Metallic radii is basically can be seen in the case of metals. We do have sodium, copper, cobalt, magnesium, है ना? So we have so many number of metals in the periodic table. Even 80% of the elements in our periodic table are actually metallic. So when we are talking about the metals, then what we could see, guys, in the metals there is a close packed structure. The atoms are closely packed. है ना. So here the atoms are very very closely packed. So let me say that this is my any of the metal, so where all the atoms, let's say here let me take the sodium atom. So all the sodium atoms are very 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 tightly and closely packed. So this is the closest distance between the two sodium atom, and yes, they cannot overlap between each other. There is no covalent bond formation. They are just tightly packed structures. Okay, so the distance between the nuclei of this sodium and this sodium will said to be d, and the half of the distance between the two nuclei of the two sodium atoms will be considered as to be the d by 2. Okay, will be considered as d. So the half of the distance will be considered as the radii in the case of the metals. So when we will be having the metals, we can determine the metallic radii. Okay. Now, van der Waals radii. Van der Waals radii can be determined in only such compounds which are not bonded by any chemical bond. So, what are such molecules? Such molecules could be helium, neon, argon, all the noble gases, because all these noble gases, when I am talking about noble gases, all these noble gases, they are inert. They do not react. Okay, they are gases. They remain away from each other. They don't do any chemical bond formation. They are just coming closer because of the physical interaction. Just like that, if I will be having two things, okay, so in between this mic and in between this mouse, there could be any kind of chemical force? No, no, there could not be any chemical interaction. There is no exchange, loss or gain of electron. There can only be the physical interaction. So when these two species, when these two objects are coming as much as close to each other, so the minimum distance, when they are at a minimum distance from each other at that particular time, the distance between the nucleus of these two atoms, let's say this is our neon and this is a neon, so the distance between the nucleus of these two neon atoms will be considered as to be d, and if we want to determine the van der Waals radii, we will do d by 2. Okay, so this is a very very easy way to find out the van der Waals radii. Now what do you mean by the ionic radii? So let me tell you guys, we do have atoms. Okay, so atom can be ionized. Okay, so when there will be a loss of electron, when I do the loss of any of the electron, this will become Na positive. Okay, so here you can see that in the case of Na we have 11 protons and we do have 11 electrons. Okay, but here in the case of Na positive, we will be having 11 protons and only 10 electrons. So effectively you will see that the proton, so because of the proton we do have a positive charge, so here the positive charge is greater rather than the number of electrons. So ultimately we could say here the nuclear charge is greater. Here we do have a high nuclear charge, and because of the high nuclear charge, that is the positive charge which is present in the nucleus, is said to be the nuclear charge, and because of the high nuclear charge, the nucleus will try to attract the large shell electron tightly, and because of that reason the size decreases. So here you can see that the size of Na is bigger but the size of Na positive is smaller. So what's the reason for that? The simple reason, the effective nuclear charge increases. The nuclear charge increases. So since the nuclear charge increases, the size decreases. Now what happened in the case of chlorine? If you will talk about the chlorine, this is basically having the 2 10 18, so this comes just before neon. So here the number of protons are going to be 17 and here the number of electrons are going to be 17. But if you will be talking about Cl negative, Cl negative can only be formed by the addition of one more electron. So here the number of protons are 17 but the number of electrons are 18. So there is an increase in electron, there is an increase in number of electrons. Okay, so when there will be an increase in number of electrons, the electron repulsion increases. Electron repulsion. So what do you mean by the electron repulsion? Guys, if there would be a more number of electrons, so you know electrons are like charges and like repel. So when they will be doing a repulsion, then the electron cloud will get dispersed, and when the electron cloud will get dispersed, the size increases. So because of the electron repulsion increases, the size of the anionic species increases, and here because of the nuclear charge increase, the size of the cationic species decreases. Okay, here the size of anionic increases. Are you getting this point? Okay, so let me tell you again. So by calculating all such radii, that is the covalent radii, the metallic, the van der Waals and the ionic radii, we will be able to find out the exact or approximate atomic size of an atom. Okay, so if you would see the comparison between the van der Waals radii, metallic and covalent, you will come to this conclusion. That is, in the case of the van der Waals radii, the atoms are coming as much as close to each other. So the van der Waals radii can be determined by this distance, that is this d by 2. Okay, when you are talking about the metallic radii, they were in close contact with each other, and so therefore the metals are hard and brittle. So the distance between these two atoms is going to be d, and this is going to be d by 2. And if you are talking about the covalent radii, there was an overlap. Because of that overlap, these two nucleus are coming more close to each other, and so therefore the distance is d by 2. Okay, so here you can see that here, if you will try to imagine, this is a bigger line showing big D. This D is getting little bit smaller because the atoms are coming little bit more closer and they are even overlapping, so this distance is decreasing as well. So as the D decreases, of course the R decreases. So we can say that the van der Waals radii is bigger in size as compared to the metallic radii than the covalent radii. Yes, the ionic radii is not comparable with these radii. Okay, ionic radii can only be compared with the metal and its ion. Okay, in the ionic compounds, the metal and its ion, this can only be compared between the metal and its ion. So before moving forward with the irregularity or the trend, I want to tell you one more thing, guys. Whenever we talk about the atomic size of an atom can be determined by two factors. One is the nuclear attraction, which I would be writing as Na, and the another will be the electron repulsion. Okay, electron repulsion, and many a time I would either be writing this as EER, and this as Na, that is nuclear attraction. Okay, so what do you mean by that? If you would see the structure of an atom, you will find that here we do have a nucleus which is positively charged in a very small size core nucleus, and we do have so many number of electrons which are present in these particular shells. Okay, so many number of electrons which are present in these shells. So what happens is, a nucleus always wants to attract the last shell electron towards itself, and it is going to determine the size of an atom. So when a nucleus tries to attract the last electron towards itself, this is known as the nuclear attraction. At the same time, these electrons which are present within a shell or in between different shells, they repel. Why they repel? Because they are the like charges. So this electron and this electron can repel. This electron and this electron which is present in the same shell can also repel. This electron can also repel. So here and within these shells, we do have a repulsion between the electron and electron, because they are the like charges, they keep repelling. So there are two forces which are working simultaneously. One is the attraction and the another is the repulsion. So we need to determine whether which is more predominating, whether the attraction is more or the repulsion is more. Okay, so much of the nuclear attraction is getting compensated by the electron repulsion. So we need to determine that which is more predominating, whether the nuclear attraction or the repulsion. Because when the Na increases, when the nuclear attraction increases, the attraction towards the last shell electron increases, the size decreases, the size becomes smaller. Okay, because the nucleus attracts this electron more strongly, more tightly. And when the electron repulsion increases, when the repulsion between the electron increases, the electrons will become more dispersed. The electrons will get more dispersed, and when the electrons will get more dispersed, the size increases. So this is a simple phenomena that we have to evaluate. Okay, that what is happening in between the nucleus and the electron, which is greater. Okay, so guys, when this nuclear attraction, so there is a decrease in nuclear attraction. So we can say one thing. So what we can say, that there is a decrease in nuclear attraction. there is a decrease in nuclear attraction. Why there is a decrease in nuclear attraction? Because of the repulsion, because of the repulsion between the inner shell electrons, so there is a decrease in nuclear attraction. The nuclear attraction ultimately decreases because of the repulsion, because at the same time they are repelling, so this nucleus will not be able to attract this last electron. Okay, there is a decrease in nuclear attraction because of the repulsion between the inner shell electrons, and this is known as this decrease in nuclear attraction is known as shielding effect. So if you want to know more on the shielding effect, you can watch out my another video which is specifically on the shielding effect and the Z effective, that what is the effective nuclear charge. Okay, so because there is a decrease in nuclear attraction, so we can say that the decrease in nuclear attraction, that is the effective nuclear charge, है ना, this is known as the effective nuclear charge. So because of the shielding, so these electrons, what are they trying to do? So because of this all repulsion between the same shell electron or between the another shell electron, when they repel, so because of this repulsion, they are trying to protect the last shell electron from the effect of a nucleus, and this is known as shielding effect. So these electrons are trying to shield. Okay, and when they do a good shielding, the size increases, and when they do poor shielding, the nucleus will be able to attract the last shell electron more tightly and the size decreases. Okay, so that will be called as the Z effective. Okay, so we want to determine that what is the effective nuclear charge. Okay, so this is it. Now moving ahead, guys, let's talk about the atomic size. So when we will be talking about the atomic size along a period and along a group, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, they all belongs to period number 2. Okay, and here I did a question mark over the neon. Why? As you can see that lithium to beryllium, boron, carbon, nitrogen, oxygen and fluorine, there is a decrease in size. The size is decreasing. Why? Because there is an increase in number of protons. The atomic number is 3, 4, 5, 6, 7, 8, 9 and 10. So as we will be moving ahead, the number of protons increases. Here we have 3 protons, here we have 3 electrons, 4 protons, 5 protons. So the number of protons are increasing. So as the number of protons are increasing, the effective nuclear charge is increasing, that is Z effective. Z effective is basically effective nuclear charge. Okay, so the effective nuclear charge means the charge which is after the repulsion between the inner shell electrons. Okay, that is this effective nuclear charge. So here the Z effective increases because as the number of protons increases, the effective nuclear charge increases, and so therefore the size decreases. Okay, but here we could see that the neon is bigger in size. The fluorine is smaller, but the neon is bigger. Why? Because in the case of neon, we do have a van der Waals radii. That's the reason why neon is bigger, not smaller than that of fluorine, because of the van der Waals radii. Clear? Now what happened when we move from top to bottom? When we move from top to bottom, lithium, sodium, potassium, rubidium and cesium, you can see that there is an increase in size. Why there is an increase in size? Because here we have a 3s3p orbital, but here we have a 2s2p orbital, here we have a 3s3p orbital, here we have a 4s4p orbital, here we have a 5s5p orbital in this particular period, and here we have a 6s. So here the number of shells are increasing, second shell, third shell, fourth shell, fifth shell, sixth shell. So here the number of shells are increasing, therefore the size increases. Predominantly the size increases. Okay, so left to right and top to bottom, the reasons are absolutely different. Okay, from left to right, the Z effective is the reason, and from top to bottom, because here in the when we are moving from top to left to right. This is also 2s2p, this is also 2s2p, this is also 2s2p, this is also 2s2p. So they all belongs to period number 2. So there is no change in the shell. There is just a change in the number of protons and the electrons. And so therefore the Z effective increases, the size decreases. I hope the point is very, very clear to all of you. Now let's focus over that what is the irregularity in the group 13 elements. So when you will see the group 13 elements, you will find that the irregularity is something like boron to aluminium. The size, absolutely, we are moving from top to bottom, that is along a group we are moving. Along a group we are moving, and along a group the number of shell increases. Here we have a 2p1, this is 3p1, this is 4p1, this is 5p1, and this is 6p1. So here it is expected the size has to increase, but what we found is boron to aluminium the size is increasing, but aluminium to gallium the size is small. So why the size is small? What has happened with the gallium? So in the case of a gallium, we do have a Scandite contraction. So what do you mean by the Scandite contraction? Let me tell you in brief. Guys, when you are moving from boron to aluminium and gallium, here in the case of gallium, when we have a 4p orbital, we do have a 4s2 3d 0, we do have a 4s2 3d0 and 3d10, 4s2 3d10 and 4p1 electronic configuration, right? While in the case of aluminium, we just have 3s2 and 3p1 as the electronic configuration. Okay, if you will be talking about the 3p1, and here also we were having 3d, but it was 0. So what is the difference between the two? And here if you would see, this is 2s2 2p1 and there was no 2d. There is no such orbital which is 2d. There is no 2d orbital. So here we have 2s2 2p1, here we have 3s2 3p1 and the 3d was vacant, but here we have 4s2 3d10 and 4p1. So here we have the extra d10 electrons. So what are they doing? Actually this is a game changer. Absolutely guys, this is a game changer. So these 10d electrons are basically poorly shielding. They are doing a poor shielding. They are causing a poor shielding. There is a poor shielding caused by 10d electrons. Poor shielding. If you would look for the shielding effect, I have also discussed this topic in one of my another session. If you will look for the shielding effect, then you must know s orbital shields very strongly, then the p orbital, then the d orbital, then the f orbital. So here we do have a d orbital, and in the d orbital we do have 10d electrons. So these 10d electrons, okay, so if I am having a nucleus and these are my shells and this is my last electron, and here I am having the 10d electrons, and these 10d electrons are poorly shielding. What they are poorly shielding? They are poorly protecting my last electron from the effect of a nucleus. So if they are poor in their work, if they are poor in protecting my electron from the effect of a nucleus, then what will happen? This nucleus will attract this electron towards itself very strongly, and so therefore because of the poor shielding caused by the inner 10d electrons, when this electron will get attracted more strongly by the nucleus, this electron will come closer to the nucleus, and so therefore the size decreases. So this has become the reason in the case of a gallium the size decreases. And why? Which d10 electrons they are? These are the 10d electrons of the Scandite series. 10d electrons of 3d series. 3d series is basically the Scandite series. Okay, let me show you a periodic table. You will be able to focus. Guys, here you can see that this is the boron, this is the aluminium. Okay, there was an increase in size, but suddenly before gallium, there was the addition of these 10d electrons, and these 10d electrons are poorly shielding the last electron from the effect of a nucleus. So if they will be having a poor shielding, then our nucleus will strongly attract the last electron towards itself, and so therefore the size decreases. And here, because of this 3d series element, the first element is the Scandite element, scandium. So that's how this is known as the Scandite contraction. So there is a contraction, there is a decrease. So this decrease is known as the Scandite contraction. So in one simple word, you can say that this is the Scandite contraction or the poor shielding caused by the 10d electrons. Okay. Now, moving forward, so here we can say that this group number 13 elements are basically this group number 13 is the most disturbing group. Why this is most disturbing? Let's see one more case. So the another case is between the indium and the thallium. So when you will compare, when we are moving from gallium to indium, the size has to increase. Yes, there is an increase in size. But when we are moving from indium to thallium, there must be an increase in size as the number of shells are increasing. But no, it is found to be almost same. Almost same. There is no much increase in size. Why there is no such increase in size? Guys, because here if you will be looking for the 6p orbital, the electronic configuration comes out to be 6s2, 4f14, 5d, 5d10, and then we have 6p1. So here we have 4f14 and 5d10 electrons. So we do have d electrons as well, and we do have 14f electrons. So these are the additional 14 electrons. And you know, as I told you, the shielding effect, if you will see the shielding effect, the f orbital is very, very poor shielding effect. This means that the f orbitals, the electrons are so away from each other that they don't shield our last shell electron from the effect of a nucleus, and because of that certain reason our nucleus attracts the last electron more strongly. Okay, so just like that, if there is a rain and you don't have an umbrella to protect yourself, what will happen? You will get wet now. Okay, so what this umbrella is acting as? This umbrella is acting as a protection. This umbrella is acting as a shield. Okay, so if that umbrella will properly shield you, you will not get affected by the rain. If that umbrella is not properly shielding you or protecting you against the rain, then you will not get protected. Okay, so it is acting as a shield. They must have act as a shield. Okay, they are in between, so they must have act as a shield. But here, because we when we do have n is equals to 6, we do have 4f subshells, and in the case of the 4f subshells, if we do have 14f electrons, and which are very, very away from each other, and they are not protecting my last electron from the effect of this particular nucleus, then what this nucleus will do? If they are not working well, then this nucleus will attract the last electron more strongly, and so therefore the size decreases. So the size, we were expecting that the size has to be something somewhat like this, but no, the size decreases. So what is the reason behind it? The reason is poor shielding caused by the 14f electrons. So that's the reason. Okay, and here we can say that the poor shielding caused by the 10d electrons, which is known as the Scandite contraction. I hope you got my point. If you will again look for the periodic table, you will find it very easily. So here Bal, yani ki this is boron, this is aluminium, this is gallium, the size decreases because of these 3d electrons, and here the indium, the size again increase, but in the case of the thallium, the size becomes the same. Why the size becomes the same? Because suddenly there was a D series, but suddenly this F block series has entered. So here you know now, after barium, after La, we do have this F block elements. So because of these 14f electrons, there is a poor shielding, and because of this poor shielding, the Z effective increases, or we could say because of this poor shielding, the Z effective increases and the size decreases. Okay, the size of the thallium decreases. Okay, so I hope you understood the group 13 elements irregularity. Now what happens in the case of the 3D series, the irregularity in the 3D series. The 3D series, if I will be talking about, these are basically the period number 4 elements, right? In the period number 4, we do have a 3D series, that is n minus 1D series. Okay, we do have scandium, titanium, V, SCTI, V, CRMN, FeCO, NiCu, and Zn. So scandium is 3D1. Okay, we could write it like 4s2 3D1. This is 4s2 3D2. This is 4s2 3D3. This is 4s1 3D5. This is how much? This is 4s2 3D5, and this is 3D6. 4s2 3D6. This is 4s2 3D7. 4s2 3D8. This is 4s2 3D 4s1 3D10, and this is 4s2 3D10. Okay, so these are the electronic configurations. I hope you already know about it. So now let's come to the size. So if I focus over their size, then what happens is that in the case of scandium, we do have only 3D1 electron. Okay, so here the atomic number is 21 only. This is 22. So the atomic number is increasing, and we do have the fourth shell only. Okay, so their sizes has to be comparatively, there must be a decrease in size. If you would be talking about what is our expectation was that there must be a decrease in size. When we are moving from left to right, the size must decrease, but actually this is not happening. The size is first decreasing. You can see the size is first decreasing, then it is becoming constant, and then there is an increase. I may call this by a boat form. I usually say that this is a boat form: decrease, constant, and increase. So there is a formation of a boat. You can remember this like this. Okay, so first the size will decrease, then it will remain constant, and then there will be an increase in size. So what is the reason behind it? So initially, in the case of scandium, titanium, and the vanadium, the nuclear attraction is greater than the electron repulsion. Reason being, the number of protons are increasing, the electrons are like 3D1, 3D2, 3D3. There is no repulsion, only attraction. Okay, so here we can say that the nuclear attraction is greater than the repulsion. So when the nuclear attraction is greater, the nucleus is attracting the electron more tightly, definitely there will be a decrease in size. Okay, that's the reason. Now what is happening between Cr to Co? So guys, here we can see that this is 3D5. 3D5, so how you can fill the 3D5 electrons? 1, 2, 3, 4, 5. We have 5 subshells, 1, 2, 3, 4, 5. So after 5, when you have to fill 4s2 3D5, 4s2 3D6, now there is a attraction. Of course, when we are moving from left to right, the Z effective is increasing, but at the same time, the repulsion also increase. So we were expecting Mn2Fe, more nuclear charge the nuclear charge is increasing, but at the same time electron repulsion has also increased. Why? Because now the electrons will try to pair up. See, if you will be entering into the 3D series, 3D6, then there will be a pairing of electron. When you will be entering into the 3D7, there will be more pairing of electron. So gradually what happens, when we start pairing up the electron, these electrons are like charges. This is also electron, this is also electron. So they start repelling each other. So once they start repelling each other, so here the electron repulsion increases. So here we found that the nuclear attraction gets compensated by the repulsion. The amount of nuclear attraction is increasing, the repulsion is increasing. So both were getting compensated. Okay, that is from Cr to Co. But as we were moving from NiCu-Zn, here what happens? Here we have 3D8, means we do have 1, 2, 3, 4, 5, 6, 7, 8. Now more number of electrons are pairing up, and so therefore more repulsion is increasing. 3D9, more repulsion. 3D10, more repulsion. So as you are adding more number of electrons, there is more repulsion. So here we can say that in the case of Ni to Cu and Zn, the electron repulsion increases, and so therefore the size increases. Okay, I hope you got the point. Why there is a decrease, why there is a constant, why there is an increase? Decrease because the nuclear attraction is increasing. Definitely, as we move from left to right, the atomic number increases, more number of protons are getting added, they are more powerful, they will be having more power over the last shell electron, and the size decreases. Here in the case of the Cr, Mn and Fe and Co, the nuclear attraction gets compensated by the repulsion. Attraction is also there, and slowly the repulsion increases, so it gets compensated, so they are almost same in size. Then after, from the NiCu-Zn, there is a there is a marginal, there is a much increase in the electron repulsion, and so therefore the size increases. I hope you got the irregularity of the 3D series elements as well. Now here comes the last irregularity in the 4D and the 5D series. So we have already seen the 3D series. Now we will be focusing over the 4D and the 5D. What happens? So first of all, guys, now we are going to do a comparative study, that is top to bottom. Okay, that is when we will be moving from top to bottom. Then what is happening? This is 3D, this is 4D, this is 5D. So this is our expectation that number of shells are adding. So when the number of shells are adding, the size must increase. Size must increase. But is this actually happens or not? Let's have a look. Guys, here when you will be moving from SC to Y and LA, here we know that this is 3D1, this is 4D1, and this is 5D1. So yes, there is a increase in size. SC to Y to LA, there is a increase in size. Got it? There will be a increase in size. Now, as soon as you move from titanium, this becomes 3D2, this becomes 4D2, and this becomes 4F14 and 5D2. So here between LA and HF, there comes the F block element. There comes the F block element. And if something is coming in between, definitely they are going to do something and something. So what happens there is, as we are moving from titanium to zirconium, there was no disturbance. So yes, of course, titanium to zirconium, the size has to increase. But as we were moving from zirconium to hafnium, then before hafnium, there is a 14 F block elements. We do have 14 F electrons. And what these 14 F electrons will do? Because of those 14 F electrons, there will be poor shielding, because F orbital do a very poor shielding, and because of this poor shielding, there will be a decrease in, the Z effective increases. The shielding becomes poor, then the nucleus becomes more powerful. The nucleus will be able to attract the last electron more strongly. So here we could say that the nuclear attraction increases. So because of the poor shielding of 14 F electrons, of this 14 F electron shielding is known as the lanthanoid contraction. Why this is known as the lanthanoid contraction? Of course, they are followed by the lanthanum now. So here LACE, that is LACE, PR, ND, all those F block elements we do have. So this is our lanthanoid series, and so therefore this is known as the lanthanoid contraction. So because of this lanthanoid contraction, because of the poor shielding of these 14 F electrons, because of this lanthanoid contraction, the size decreases. So here we were expecting that titanium you are this much, zirconium you are this much, hafnium you have to increase. But hafnium says that no, it's not in my hand. Because of this lanthanoid contraction, I am getting contracted, and so therefore the size of hafnium becomes almost equal to that of zirconium. Okay, almost equal. So that's how I have written that zirconium is almost equal to that of the hafnium. You got the point? I hope, because when we will be moving from zirconium to hafnium, just before hafnium there is a 14 F electrons, and these F electrons are doing a very poor shielding, and because of their poor shielding, the nucleus becomes more powerful and will attract the last electron more firmly, and so therefore there will be a decrease in size, and that decrease is basically the contraction. Okay, and so therefore the size of hafnium becomes as much as equal to that of the zirconium. The same thing happens because these F electrons will cause this effect with the impact will be faced by all the elements which are after lanthanoids. Okay, so here also this will happen. Vanadium to nobelium, there will be an increase in size. V to NB, there will be an increase in size, but when you will compare between the NB and TA, the size becomes almost the same. The reason is the same. Lanthanoid contraction is the reason. Cr2MO, the size increases, but MO and W, the size all becomes almost the same. Mn to Tc, the size increases, but Tc and Re, the size becomes the same. Fe to Ru, the size increases, but Ru to OS, the size becomes almost the same. The reason is lanthanoid contraction. CO2RH, the size increases, but here the rhodium and iridium will be having almost the same size. Similarly here, and similarly here. Okay, so ultimately we can say that if you would be comparing between the La and HF, if you are comparing between these two elements, which two elements? These two elements, La and HF, the size is going to be much smaller. Why? Because there are 14 F block elements which are showing a contraction in size. So after La, we do have all those 14 electrons which are showing a small in size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and there comes the hafnium which is smaller, Got it? So of course the hafnium has to be smaller. This hafnium has to be smaller. Let me draw it again. Smaller. Okay, so because after 14F electrons this hafnium is going to be, so this becomes smaller. So La and HF, yes, hafnium is much smaller than that of La. If you will be comparing between the copper, silver and gold, yes, of course you got it right. That is from the copper to silver the size will increase because there is an addition of shell, but Ag to Au the size remains almost the same because the reason is lanthanoid contraction. Similarly, between the Zn to Cd, the size increases, but Cd to Hg, the size becomes almost the same. So this is it, guys. So we can conclude that there is a general trend in the atomic size when we are moving from left to right, top to bottom, left to right, we see Z effective increases, the size decreases, but as we move from top to bottom, the N number of shells increases, and so therefore the size increases. Okay, but there are some irregularities which could be seen with the noble gases. In the case of the noble gases, their sizes are incomparable because they have a van der Waals radii, while other elements are not having the van der Waals radii. They have been calculated by their covalent or metallic radii. Okay, so van der Waals radii, the size is going to be, of course, it is going to be bigger. Okay, the another irregularity that we have seen in the case of the group 13 elements, boron to aluminium, the size increases but gallium becomes smaller because of the Scandite contraction. Then the indium size increases but the thallium it becomes the same. The reason is the lanthanoid contraction. Then the irregularity can be seen in the 3D series elements, which I told you by the boat form. There is a decrease, the size will remain almost the same. Then there is an increase because of the repulsion. There is a electron-electron repulsion. There is a nuclear attraction. The size decreases because of the electron-electron repulsion. The size increases. And when you are talking about the 4D and the 5D series, so post-lanthanoid elements, post-lanthanoids, we have seen that 4D and the 5D series are having almost the same size. Why the size of the 4D and 5D series is same? Because of the lanthanoid contraction, the size becomes the same. But if you will be talking about the SCY and LA, there is no low lanthanoid series, no 14F electrons, they will come afterwards. Okay, so here there is an increase in size. So this is it, guys. If you really enjoyed watching this particular video, then thank you so much. Like, subscribe and share this session with your companions, with your peers, and do follow me on an academy for more updates on my courses. Thank you. Have a great day.